In this video, I'm going to describe two examples of calculating with the Biot Savart law for how to calculate magnetic field at some place in space due to a current distribution. So in this example, the first example of the two different examples, I've got a coordinate system. You can see there's an XY coordinate system. And I want to know what is the magnetic field here at the origin of the coordinate system. And I want to know what is the magnetic field at this place due to a very strange current distribution. The current is coming down from the positive y-axis from way out at infinity, coming down and just getting closer and closer and closer until it gets within this radial distance, capital R, away from the origin. Then it takes a circular arc, so it stays the same radial distance away, but transfers over to the positive x-axis, and then again runs away to infinity along the positive x-axis. And everywhere along this particular wire is the current I. So let's say that the radius of curvature is 4 centimeters. So this is, some small arc. And the current, we can just give it a value, say 2 amps. So we've got a very, very particular problem. The wire with this sort of circular curved bend in it is infinitely long, but there is a finite current along it. Right? So there's a finite current. The current's the same everywhere along the wire. It comes in from positive infinity on the y-axis and goes out to positive infinity on the x-axis. And we want to know what's the magnetic field at the origin due to this current distribution. Okay, so the answer depends on using the Biot Savart law. So the Biot Savart, I'll just write it down, mu naught I over 4 pi ds cross r hat over r squared. Okay, so in order to figure out how to use Biot Savart, so in order to figure out how to use the Biot Savart law, let's explore our problem by picking a few representative DS segments. So the few that I would pick, so maybe I'll outline them in, say, red. So here's a DS segment from here to here along the wire, right? So there's a DS. Here's another one from here to here along the wire. And here's another one. Can you see that they're all in different directions? This DS segment is down. This DS segment is mostly towards the right, but a little bit down. This DS segment is mostly down, but a little bit towards the right. And then here's another one. This DS segment is strictly towards the right. But that's just picking different places along the wire and asking which way is the current flowing. That's what DS is. Pick a small segment of the wire and give it the direction in which the current is flowing, right? The conventional current. Okay, so those are various DS segments, but in order to figure out how Biot Savart is going to run, what I really need to pay attention to is let's look at what ds cross r hat looks like for these various DS's that I picked out, right? So the DS's along the y-axis, they all kind of look the same. They're just little short sections, but they point downwards only. Along the x-axis, they're little short sections that only point in the positive x-axis. But the ds's along the curve are interesting because as I move along the curve, the ds's change direction. But what about r hat? So let's make r hat in, say, purple, right? So r hat, remember, points at P from ds. So here is ds, and to our first ds, and P is down here at the origin. So r hat points down, right? That's how you get from this segment to the origin. The way you get from this segment right over here to the origin is actually you go that way, right? You have to go towards the negative x-axis from this segment. From this segment, you have to go towards the negative y-axis to get back to P. But from this segment that's along the circular arc, r hat is that way. And from this segment, which is further along the circular arc, r hat is that way, right? So you can begin to see that ds cross r hat is something that I need to think about for each of these four different segments. If you think about ds cross r hat for this first segment up here at the top, ds cross r hat is 0. And that's because ds and r hat point in the same direction. They're parallel. And if you remember from our cross product right-hand rule video, if the angle between the two vectors in the cross product is 0, that is they're parallel, they point in the same direction, then their cross product is 0 because you're taking the sine of 0 as the angle. In this case, though, ds cross r hat is equal to 0 again, but it's not because they're in the same direction. They're actually anti-parallel over here. You can see the ds vector is towards the right, the r hat vector is towards the left. So again, ds cross r hat is 0 if you go out along the x-axis. So as you come in along the y-axis, ds cross r hat is 0, and as you go out along the x-axis, ds cross r hat is again 0. So let's keep that in mind. And in this case here, these two ds cross r hats are going to be similar. Can you see that in the case of this little piece of wire right here, can you see that ds is sort of towards the right but a little bit down? But r hat is perpendicular to it because r hat points along the radial direction from this circular arc, right? This is a piece of a circle. The r hat vector points along the radial direction. The ds vector points along the tangential direction, and tangential to radial is perpendicular. So ds cross r hat, in that case, is not 0. So I'm going to say that we need to worry about it because it's not 0, right? When things aren't 0, you have to worry about them, but when things are 0, you can not worry about them when you're thinking about integration. The same thing happens here. Can you see that ds points more down than towards the right over here, but r hat points perpendicular to it, points towards the origin. So this points tangential to the origin, and this points radial or towards the origin. So those are at 90 degrees to each other. So this other segment is also a ds cross r hat that gives not 0. So when I imagine integrating up all of the small contributions to the magnetic field to get the net magnetic field at P, so this is the small contributions at P, right? All I need to do is integrate along the circular arc, right? Because ds cross r hat along the straight line sections, ds cross r hat is just 0. And when you add 0 to a summation, to an integral, it doesn't change the value of the integral. So you only have to go along the circular arc, right? So dB due to ds segments along x and y axes do not contribute. So I only have to do my integral along the circular arc. So that's good. I learned something by doing this exploration, right? The exploration involved just picking various ds's and wondering, how is Biot Savart going to treat each of these various representative ds's? Okay, so along circular arc, ds is perpendicular to r hat, which means that ds cross r hat is going to have a magnitude that's equal to ds r hat times the sine of 90 degrees, right? Because ds and r hat are at perpendicular. But the sine of 90 degrees is 1. The magnitude of a unit vector is always 1. So the magnitude of ds cross r hat is always just the magnitude of ds, right? This is along the circular arc. So what is the magnitude of ds, though? The magnitude of ds for circles, right? So here is that place P, and here is the circular arc. If I imagine a small sector, right, where the angle is d theta and the radius is r, then the arc length, right, the distance from one end of the angle to the other end of that little piece of pie is r d theta, right? The small arc length is r times the small angular span, right? This is a basic statement about the relationship between the circumference and the radius. It's actually essentially the definition of the radian is in here. So anyways, so the length of ds is a vector whose magnitude is equal to r times the amount of angle sweep, right? The angle is swept out as you go from the beginning to the end of any of the ds arc lengths. All right. So now I understand the magnitude of ds. But what about the direction? Because ds is a vector. Or actually, so sorry. Actually, I want to know what's the direction of ds cross r hat, not the direction of ds, excuse me. So what I really want to know is not the direction of ds, but what's the direction of ds cross r hat, right? I know its magnitude is r d theta, but I want to know what's the result of the cross product. And in order to do this, you have to use the right-hand rule. So you go in and you have a few representative ds's to check. And if you look at ds cross r hat on this first little arc length right here, right? If you use the right-hand rule, what you're going to find is ds cross r hat from this first segment is actually the negative z direction. It's negative k hat. So that's what you get for the first segment right here. But can you see that if you go and you check the second segment, you're also going to get negative k hat. And if you check a segment in between, you'll get negative k hat. And if you check a segment afterwards, you'll get negative k hat. But if you check along the straight lines, the truth is that's where it was parallel and anti-parallel, and the cross product was 0 anyways. So it doesn't matter to check out here what's the direction, because frankly, there's not a direction defined. There's only a direction defined when the cross product is not 0, right? So, and it turns out that the cross product everywhere along this circular arc, everywhere along there, the cross product is the same value, actually, negative k hat. Okay, so ds cross r hat has magnitude rd theta and direction negative k hat everywhere along the arc. So now we can update our Biot Savart. It's mu naught I over 4 pi ds cross r hat, right? Let me just actually, so that's the full Biot Savart. So let's fill in the details we know. So it's mu naught I over 4 pi. ds cross r hat is rd theta. The direction is negative k hat. So I'm going to put, I'll just multiply it, right? And then also, don't forget, there's a division by r squared. R, remember, is the distance between our little segment and the place where we want to know the magnetic field. And as we go along this arc, actually, that distance for all of the small arc lengths along that edge of the circle is the same distance. It's the distance capital R. So actually, I'm just going to end up dividing by r squared. And that is the contribution to the magnetic field from each small angular sweep along that circular arc. So now, the net magnetic field at P is going to be equal to the integral mu naught I over 4 pi times negative k hat. So I'll just move that unit vector direction over, right? Because it's just multiplied and you can move the stuff around. And then capital R and divide by r squared is 1 over r. So it's d theta over capital R. And the integral just goes over the arc. So the way you go over the arc is you go from angles, right? Let's say you start at angle 0, which is this direction, and then you sweep to this angle and this angle and this angle, this angle, this angle, that angle. That's a sweep through 90 degrees. But whenever you integrate with angles, you must use radians. If you integrate with an angle, you have to use radians, or else actually you don't get the right answer. So use radians. So 90 degrees is the same as pi over 2 radians. This is important, right? You don't know what it means to essentially multiply by small amounts of degrees. Degrees is a little artificial. Degrees is, that's like an ancient thing. Radians is a geometric sort of distance connection to angle sweep. That's the usefulness, and that's the sort of practical point of the radian. So when you integrate over an angle, the truth is you have to use radians. Okay, so here we go. If I want to integrate this, right, the only thing that depends on the angle is d theta, so everything else is a constant. So the net magnetic field at the position P is mu naught I over 4 pi. It's got the negative k hat, right? Because remember that the net magnetic field is going to be a vector, so I've got to have vectors being added together. And then I've got the 1 over r, right? And then the integral of d theta from 0 to pi over 2 is just pi over 2 radians. Okay. So let's do a little bit of algebra cleanup. So the pi's cancel. Boom, boom. And I've got, I guess that's all. And then the 4 and the 2 can make an 8. So I'll knock out the 4 and the 2 and replace them with an 8. Okay, so then let's see what we got. So B net at the position P equals mu naught. So let me just do that. So mu naught I over 8R, like that. And then negative k hat. All right. So this is my expression. I can actually evaluate all this. This was 4 pi times 10 to the minus 7th Tesla meters per amp. R was 4 centimeters. That was early on. I gave you some physical data to imagine. And the current is 2 amps. So let's stick all this stuff in. So the magnetic field is, so mu naught is 4 pi times 10 to the minus 7. Have Tesla meters per amps. And then the current is 2 amps. 8 times R, 8 times 4 centimeters, right? So that got divided. So I've got everything in there, and then I multiply by the direction, negative k hat. So we can continue to cancel some stuff. So let me take out a different color to keep it straight. So here's the 4, knocks out that 4, but it doesn't knock out the centimeter. The amp and the amp knock each other out. The meter and the meter knock each other out, but not the centi. Be really careful. And the 2 and the 8 knock each other out to leave a 4 downstairs. Okay, so the only stuff I have left over at this point, I have a factor of pi. I have a factor of 10 to the minus 7. I have a Tesla. I have a factor of 4 on the bottom. And then I have a factor of centi, which is 10 to the minus 2, right? And then I have a negative k hat. Yeah, so I have this stuff. So 10 to the minus 2 on the bottom is 10 to the positive 2. 10 to the positive 2 times 10 to the minus 7 is 10 to the minus 5. So this is pi over 4 times 10 to the minus 5 Tesla negative k hat. And this is the magnetic field at P. Right? I've got no unknowns. I've got a direction. I have Tesla. I calculated magnetic field, so the strength needs to be in units that are magnetic field units and no other units, right? All the other units are gone. Yeah, boom. So that's our first example. The second example, I'm not going to do so much calculus, but I am going to indicate the calculus. So the second example is a long, straight wire. All right, so let me draw a long, straight wire. I'm going to draw it, I guess, in black. And I'm going to say that the current along this straight wire is I, and it's headed towards the right. Okay, so I want to know, first of all, so let me take this back down to some small value. Okay, so what is B at P, right? We want to understand what's the magnetic field of this wire. So here is a position P. And what's interesting about this position P is I actually can't tell the difference between this position P and this position P. And the reason is because if I stand here and I look towards my left and I look towards my right, all I see is a long straight wire going out to infinity. And if I look to my right, I see a long straight wire going out to infinity. But that's actually exactly the same case as if I was to stand over here or over here. As long as I am the same distance, I'll say I'm the distance r away from the wire on the top side. Okay, each of these people sees the same wire, even though they're at different locations, they're the same distance from the closest place on the wire, right? And this is an argument by symmetry, that none of these people here can see a different value of magnetism where they are standing at their position, right? So when I ask what is the magnetic field at P, it seems like it only depends on the distance away from the wire, which I'll call R, right? So I'll say distance from closest place on the wire, right, to them, right? This person right here, I'm not going to care about the distance to a faraway place because that's not really well defined. What's well defined is to talk about the closest place you are to the wire in this particular case, right? So really, actually, I'm starting to think that I need to understand what is the magnetic field as a function of distance from the wire, right? And not necessarily this kind of a question, right? So this actually is a little bit more palatable. It's a little bit more meaningful, honestly. So that's how we're going to think about this problem, as only a function of the distance away. Here's another thing, though. What is the difference between being on the top of the wire, top side of the wire, and being the same distance away on the bottom side of the wire, right? What if this is like P1 and this is P2? So what's interesting about this is actually there ends up being an interesting difference. So check this out. Let me go and erase these other people and the idea of symmetry. And let's just think about, what do these two people see? So the way to do this is, it's sort of similar to the previous example. You pick some representative little lengths of the wire. So let me pick this one. There's the ds vector. If I'm on the top side, the way that, right, so actually let me write down Biot Savart real quick. So remember that Biot Savart says that the small contribution of the magnetic field is mu naught I over 4 pi. And then it goes ds cross r hat divided by r squared. So ds, r hat, and r squared are the geometric things to worry about. Mu naught I over 4 pi, these are sort of just sort of geometrically, or these are non-geometric things. They're sort of scaling issues, actually. But the ds cross r hat is directional. Division by r squared is got to do with the distance, right, that the position P is from the wire. Okay, so on the top side, let's do the top in blue. So the top in blue, if I want to know what's the magnetic field contribution at P1, this is r hat. And actually this, actually, let me also erase. I'm so sorry to do this. It's kind of symbolically confusing all of a sudden. But this is the distance that the little ds element is from the position P, right? And if you look at this, let me remind you of what ds is. ds points in the same direction as the current, which is towards the right, but has the length, which is a infinitesimal distance, right? So it's, some nanometers. It's very, very small in calculus terms. It's infinitely small, infinitesimally long. And it points in the direction of the current. And then there's r hat. And if you do ds cross r hat, what you're going to get is out of the page. It's out of the screen. But let's switch it up and talk about the other side. Do it in purple. So the other side's down here. R hat points this way instead, right? And R is actually the same distance away, right? But it's a different direction away. And if you go and you wonder, what's ds cross r hat in this case? It's actually into the page this time. So where this person is sitting, they see a magnetic field contribution into the screen from this little red length. But from where this person is sitting, they don't see into the page, they see out of the page. That is, this person's little compass, their North Pole. Let me draw that better. Oops. Their little compass is going to point out of the screen if they have a compass where this is the North Pole and the South Pole. And this person below is going to have a compass needle that points into the screen instead. That's their North Pole and South Pole compass, right? Because compasses tell you how to get to the north and from the south, right? Yeah, so they're going to see oppositely directed magnetic field. And if you, so this is sort of hard to depict, but what if I also had another person? So let me draw this person sort of vaguely. They are sitting kind of sort of out from the screen. This is their head, the back of their head actually. And if they do their ds cross rhat stuff, then what they're going to find is they find that their magnetic field points down. And if you have a different person who is, let's say, I'll just draw them actually in black but small. So they are actually behind the wire. They're going to measure a magnetic field upwards. So if when you do ds cross rhat, you're going to get an upwards arrow. And what this looks like is if you take a person whose eyeball, the current is aimed at their eyeball, right? So you take from this person's point of view, this person sees a current headed towards them. And if you imagine this person, their left side of their body is near you and the right side of their body is far from you, right? The right side is behind the current, and the left side is in front of the current. That's their left and right. What they see on their left side is this gray arrow downwards. So, right, this is the point of view of this person here. They see a gray arrow downwards. And on their right side, which is what this person sees, they see an upward arrow. And what this person sees above is something pointing from back to front or right to left above the wire. And what this person sees below the wire is something that points from the front towards the back, from left to right instead. So they see a magnetic field that cycles the wire, right, at that radius r. Or actually, shoot, yeah, let me not say that yet. Okay, so anyways, so what you go and do is the following thing. You go, right, you find representative DS's and you just square them off and you make sure that you understand how ds cross rhat is going to work. And then you write down the Biot Savart infinitesimal rule. Then you integrate over all of the current. In the case of our problem, we have to go all the way back to negative infinity, start there, go along some axis. You could say that this is the x-axis, and you go all the way out to positive infinity. So in this case, you're going to do some negative infinity to infinity, or if you use angles, you might say that looking back down the wire, you start at the angle 0, and if you go all the way to the front of the wire, you go all the way to the angle 180 degrees, right? So if you do it in terms of angles, you might be using from 0 all the way to, remember when you do integrals with angles, you use radians. So you go from 0 radians all the way to pi radians. That's the same thing as 180 degrees. But anyways, what you're going to get is that the magnetic field has a magnitude. So this is the magnitude of the integral after the integral is finished. So you see the magnitudes on the outside of the integration symbol. And it becomes, let me actually quickly look it up because I always can never remember what the answer is. It's mu naught times I, so it's mu naught times the current that flows along this long straight wire divided by 2 pi times the distance away from the wire where you're asking for the magnetic field. So I'm going to describe it this way. Okay, so as an example, let's have a concrete example. Here's a long straight wire, goes out to positive infinity from negative infinity, and I want to know what is the magnetic field right up, or actually, let's complicate stuff. What's the magnetic field here, where this place, its closest position on the wire is, say, 10 centimeters. Nope, let's use something more interesting. How about 7 centimeters away, and the current is 0.5 amps, right? So we want to know what is the strength of the magnetic field 7 centimeters away. It's equal to mu naught, which is 4 pi times 10 to the minus 7. Tesla's meters per amp, that's what mu naught is, times the current I, so 0.5 amps, divide by 2 pi, and then also the R, and the R is 7 centimeters. All right, so if you go through and you calculate, so I like to use a different color to cross off stuff. The amp and the amp cancel. The meter and the meter cancel, but the centi is left over. Can't forget the centi. The pi and the pi cancel. The 4 and the 2 partially cancel. There's a 2 left over. And then the 7 doesn't cancel against anything. So let's collect together all the things that didn't go away. So we got a 2 divided by a 7. I got a 10 to the minus 7. And then we have a centi, which is a 10 to the minus 2, right? That's the centi. And then there's a, oh, shoot, the 0.5 and that 2. Let's go in. The 0.5 and the 2 cancel. So let me get rid of the 2 down here. Let me use an eraser. Boom. So 1 over 7. And then the units that are left over is the Tesla. Lucky for us because we're calculating magnetic field, and Tesla is the SI unit of field strength, right? So we can clean this up a little bit. It's 1 over 7 times 10 to the minus 5 Tesla. And that'll be the magnetic field at 7 centimeters, right? But the thing is, I've got a current towards the right, and I asked down here, and really what I want to know is the vector. But all you got to do is remember that the magnetic field below a current headed towards the right is into the screen, right? Or you can use the right-hand rule. So into the screen. So if this actually, let's say that the current was heading along the positive y-axis, and the person was down here below along the z direction, right? So let's put the z-axis here. And the question is, if the so the wire is heading along the positive y-axis, right? Here's the current. The question about where is down the z-axis, right? 7 centimeters below the origin, but along the z-axis, right? The question is what direction is the magnetic field in terms of I hat, j hat, k hat. The thing is you have to remember the relationship between the directions of the axes. And this is really tough to remember, but let me draw you a picture. I'm hoping that you can internalize this. So if you draw the z-axis upwards, the x-axis is to the left but out of the screen. Then the y-axis is towards the right but out of the screen. This is a right-handed coordinate system. It's right-handed because if you use the right-hand rule, you get I cross j equal to positive k. Right-hand rule, you stick your fingers of your right hand in the direction of the first vector. It's the I hat. Then you twist your wrist until the fingers of your right hand can curl over towards the second vector direction, which is y hat. The thumb of the right hand oriented that way points in the third vector, which is up the z. So this is all to say that this is not the positive x-axis or x direction, it's the negative x direction. So the magnetic field at that 7 centimeter location in these axes is 1 over 7 times 10 to the minus 5 Tesla negative I hat.